community analysis, we are looking at what these structures lie inside the graph to see how a community set behaves. A dense subgraph or a cluster within a graph is studied in which its nodes are more connected within a cluster than to the nodes outside a cluster. Okay? So by definition, a dense subgraph or a cluster is one where some nodes have higher connectivity to one another than to the other nodes. Okay? So you can find these definitive clusters in there. Cohesion is connectivity inside. How high is that? How deeply these nodes are connected to one another. And separation is connectivity between the clusters. Okay? So if they have a higher distance between the various clusters, they have higher separation and vice versa. Some of the things that we check for is we discover a community. Now, this is some static property. We look at this structure right now, or let's say without the effect of time. Then interaction with the community, again, since this depends on the edges, incomings, outcomings, interaction between communities, again, this is something that depends upon the edges or connections we have. So all of this is the static properties. We also have some temporal properties or temporal relationships. So how a community emerged or dissolved, whether it was growing or shrinking. This is something we do over time. Which communities are stable, either they are constantly shifting or constantly growing. If they are splitting, this is again something we check over time. And then prediction of a node will migrate to another community if we say that there is a possibility that one member of one community will shift to the other community. And this is something that we can measure over time. So this is part of the temporal analysis of your graph. Looking at centrality analysis, we need to understand the importance of any given node, given vertex. We check for connectivity importance. What is the degree of the node? What is the in degree? What is the out degree? And particularly the out degree. So how many other nodes can this one influence? Then we check the closeness importance. What is the average length of the paths that it has? How much time it takes from one node, from this particular node to get to the other ones? We check for betweenness importance. What is the fraction of the shortest paths that X appears in? How many nodes does this connect to? And while being the part of the shortest distance between those X and Y nodes in question. ठीक है? कितनी इस तरह की नोड्स हैं कि जिनके बीच में ये पड़ता है और ये शॉर्टेस्ट डिस्टेंस का हिस्सा है कि ठीक है, इससे होके आप कह सकते हैं कि शॉर्टेस्ट डिस्टेंस आता है. Vulnerability, if vertex X belongs to the minimum node set, then if its removal will make the graph disconnected. ठीक है, तो how significant it is कि इसको move करने से high disruption network में आएगी या low disruption आएगी. ठीक है, so this is part of understanding the importance of the node itself. One application where the centrality analysis is really required is the page rank. Okay? Importance or rank of a vertex or a page is computed as the total rank of its adjacent edges. Okay? This is eigenvector centrality. हम ये check कर रहे होते हैं कि this particular page इसकी अपनी importance कितनी है considering how many neighbors it does or does not have. Okay? So this is a real world application where we use this centrality analysis. Lastly, we have pattern matching. We check to understand if any two given graphs are equal to one another or not. Okay? We look for the directed ones, we look for the undirected ones, and directed edges, undirected edges, and we see if they provide us with the equality or not. Okay? And we try to see, given a bigger graph, if there are some parts of it that are being represented with a smaller graph or not. Okay? This pattern matching technique is used in banking fraud detection. We are seeing that the same patterns lie there or not. Then we check for these in security applications, bioinformatics, biochemistry, social networks. Again, you're applying for some job and you want to see, your employer wants to see how reliable you are, then they'll see your social network to check for what trends or patterns have you been following in all of your life, GPS and smart cities, telecom. So all of these use these pattern matching graphical analysis techniques. We should conclude by studying a little about the graph databases. We did a little of these in MySQL part as well. So graph databases represent data in graphical structures. So they are naturally they have some nodes and some edges. Node represent the entities and edges represent the relationships. Relationships are directed, okay? And we can have this semantic of direction embedded in this graph as well. Okay. So reflexivity, association, all of these can be assigned with the edges themselves. At every node or every edge, we have some key value properties, and every node or edge has some labels. Okay. And these are optimized for graph-related queries. Some of these examples are Neo4j, OrientDB, Titan, Apache Giraffe, and Microsoft Graph Engine. Now, I'd like you to study at least one of these, Neo4j, in order to better understand how these graph works and how these real-world scenarios handle these graphs. Okay, so that would be a really good exercise to incorporate a better understanding of graphs. Okay, so that's something I'd like all of you to do. That concludes our graph analytics.